Chapter 7.2, Classifying Chemical Reactions. Here we're going to talk about three different classes of reactions. First, we're going to talk about precipitation, then acid-base, and finally oxidation-reduction. So let's start with precipitation reactions. In precipitation reactions, dissolved substances react to form one or more, but typically just one, solid product. Many precipitation reactions are double replacement reactions. Sometimes these are called double displacement, sometimes they're called metathesis reactions. I will typically use the phrase double replacement reactions. So in a double replacement reaction, we can assume that the cations and the anions, they change partners. Now you got to be careful here, because if you go to predict products, you need to make sure that these ionic compounds are neutral. Once you have predicted your products properly, then you can balance the reaction equation. So for example, I may give you a type of problem where I just state in a word problem, calcium chloride and silver nitrate react with one another, predict the products of the reaction. So what you need to do here is you need to recognize that calcium chloride and silver nitrate, they are both ionic compounds. So if they're reacting with one another, they are reacting in what's called a double replacement reaction. So the ionic compounds, they essentially swap partners. Sometimes it's helpful to think of this like foil, where the outside ions go together and the inside ions go together. So calcium is going to react with nitrate and form calcium nitrate. Silver is going to react with chloride and form silver chloride. So you just need to make sure you're paying attention to the charges of these ions. So these ionic compounds in the products are neutral. Calcium is +2, nitrate is -1, so the formula here is CaNO3 Silver is +1, chloride is -1, so this would just be AgCl. So you start by predicting the products, and then you'll place coefficients in to make sure the reaction equation is balanced. Now for precipitation reactions, it is important to know which product is going to be soluble and which will be the precipitate, or the solid product. Now typically our solvent is water, so we have a list of solubility rules to help us determine which compounds are soluble. It's important to note here that compounds that are soluble get the symbol AQ. Remember that AQ means aqueous, so anything that is soluble will form an aqueous solution because they can dissolve in water. Compounds that are insoluble get the symbol S. So make sure you don't get this mixed up in your head and think that S means soluble. It does not. S means solid, so something that is a solid is therefore insoluble. Whereas AQ means aqueous, which means it dissolves in water and is therefore soluble. Okay, so this is what these rules look like. There are two pages. The first page are those ions, I should say, that are generally soluble. So how this works is you look at your ionic compound, and if your ionic compound contains any of these ions, it is always soluble. So if your compound contains a group 1 metal cation, like lithium, sodium, potassium, rubidium, or cesium, or if it contains the ammonium cation, which is NH4+, that ionic compound will always be soluble. There are no exceptions. If your compound contains any of these three halide ions, chloride, bromide, or iodide, it will be soluble unless the cation is silver, mercury, or lead. Then it's insoluble. So under the generally soluble rule, if you see that your compound has one of these ions, it is soluble unless you notice something here in the exceptions page. So for example, fluorides. So fluoride ions are generally soluble, but if your fluoride ion is with a group 2 metal cation like magnesium or calcium, or if it's with lead or iron, then that fluoride is insoluble. So for example, PbF2, lead fluoride would be insoluble and would get the state of matter symbol S. If it's got acetate, bicarbonate, nitrate, or chlorate, it is always soluble. If it's got sulfate, it's generally soluble unless it's with silver, barium, calcium, mercury, lead, or strontium. Okay. The other side of this are the generally insoluble rules. So anything that's generally insoluble, again, if you notice that your compound has one of these ions, it is going to be insoluble unless it's paired up with one of these exceptions. So any ionic compounds with carbonate are generally insoluble, and they are only soluble if they are with a group 1 metal cation or ammonium. Same thing with chromate, phosphate, and sulfide. Hydroxides are insoluble unless they are with a group 1 metal cation or barium. So these rules will be on the reference sheet. You don't need to memorize them. Again, you just need to understand how to use these rules. Okay, so let's have you do a quick knowledge check question. So I recommend you download the PowerPoint slide so you can follow along and go backwards to look at those rules. So which of the following is water soluble? Barium sulfate, silver hydroxide, lithium hydroxide, or calcium carbonate? Okay, the correct answer here is C, lithium hydroxide. The other three would be insoluble. Let's look at a precipitation reaction example. So this is a type of problem I may give you. This could also be written as a word problem. I could say potassium iodide reacts with lead nitrate, and you would need to know how to find those chemical formulas. So we've got potassium iodide, Ki, it's aqueous, and it's reacting with lead nitrate, PbNO3, also aqueous. So first thing you need to do is you need to figure out the charges on these ions and the reactants. So potassium, it's in group 1, so it's +1. Iodide is in group 7, so it's -1. NO3- is a polyatomic ion, so nitrate is -1. And then lead is a post-transition metal. It has a variable charge, but we can determine that it must be +2 since it is with 2 nitrate ions. So lead is +2 here. Now what you're going to do is you're going to try and predict the products. So you're going to assume that they swap partners. So Pb2+ and K+ switch partners. So lead is going to react with iodide and potassium is going to react with nitrate. So now to predict your products, you want to make neutral compounds by using the crisscross rule. So Pb2+ is reacting with I-. So based on the crisscross rule, the neutral compound should have a formula of PbI2. K+ is going with NO3-, so since they both have charges of 1, that compound must have a formula of KNO3. Now what you need to do here is you need to balance. So we've got Ki plus PbNO3 forms PbI2 and KNO3. So we know our products, we balanced the charges, but we need to balance our equation. In this case, we need to put a 2 in front of KNO3 to balance out the nitrate ions. Then we would need to place a 2 in front of Ki to balance out iodide and potassium. So we've got 2 Ki plus 1 PbNO3 forms PbI2 and KNO3. 2 potassiums on both sides, 2 nitrates on both sides, 2 iodides on both sides, and 1 lead on both sides. Your final step here is to predict the state of matter of the product. So you need to predict which of these compounds is aqueous, which is a solid, or which is soluble, which is insoluble. So we'll start with PbI2. PbI2 is insoluble because if you go back and look at the halide rules, halides like I- are generally soluble unless they're with Pb2+. So this is an exception, which means it is insoluble. So we would write it as PbI2 parenthesis S. Now KNO3 is a bit easier. This is soluble. Anything with potassium or anything with nitrate is always soluble. So we would write KNO3AQ. So your final answer here, the balanced molecular equation would be 2KiAQ plus PbNO3 AQ forms PbI2S and 2KNO3AQ. This is the balanced molecular equation. Now we could even take this problem a step or two further, and I could ask you to generate the net ionic equation. So make sure you remember how to get that from this point of the problem as well. Okay, and so that's illustrated here. Remember, anything that's aqueous, break it apart into its ions, cross out the spectator ions, and this is what would be left behind. 2I- plus Pb2+ forms PbI2. Okay, let's try a knowledge check question. Which of the following precipitates forms when the following reactants are mixed? So we've got magnesium acetate, C2H3O2- is acetate, plus lithium hydroxide. Alright, and the correct answer here is B, MgOH2. So you put the outside ions together, the inside ions together. Lithium would go with acetate and it would form lithium acetate, LiC2H3O2. Then magnesium would go with hydroxide. Magnesium is +2, hydroxide is -1, so that would be MgOH2. When you look at the solubility rules, lithium acetate is going to be soluble, magnesium hydroxide is going to be insoluble. So this is the precipitate that forms. Alright, next let's look at acid-base reactions. Now, an acid-base reaction is one in which a hydrogen ion, H+, is transferred from one chemical species to another. Now, you'll learn a bit more about acids and bases in Gen Chem 2, so we're just going to go over the basics, go over the overview here. We are going to define an acid as a substance that will dissolve in water to yield hydronium ions. For example, hydrochloric acid, or HCl, is a strong acid. So HCl, in its gaseous form, it's dissolved in water, so HCl gas becomes HClAQ. Then what happens here is when those HClAQ ions, they react with water to yield hydronium ions. We've got H3O plus and Cl minus. So HCl donates a proton. It donates an H plus ion to water to form what are called hydronium ions. So this is what an acid does. It dissolves in water, or it reacts with water to form hydronium ions, and then we get these left behind chloride ions. Now this is a definition you're going to have to understand: strong versus weak acids. Strong acids are acids that completely dissolve. So when we write reactions with strong acids, we use a single-headed arrow to indicate the totality of the reaction. So only products remain after the reaction is finished. Weak acids are acids that only partially dissolve. So we use these double-headed arrows to indicate the partiality of the reaction. So with weak acids, there are both reactants and products in the final reaction mixture. Okay, so let's look at an example here. A weak acid. Acetic acid, which is the primary component of vinegar, is a weak acid. So it has the formula. Typically, it's written as HC2H3O2. Sometimes it's written like this, HCH3CO2. So it reacts with water to form CH3CO2. So this is the acetate ion, and H3O plus hydronium ions. So only 1% are present in the ionized form. So for example, if I had 100 acetic acid molecules and I dropped them in water, only one of those 100 would ionize and form hydronium ions. The other 99 get left behind and stay together as acetic acid. So since acetic acid is a weak acid, it only partially ionizes. In this case, only 1% of acetic acid will ionize and form acetate and hydronium ions. If I did this thought experiment with something like hydrochloric acid, which is a strong acid, if I took 100 molecules of hydrochloric acid, drop them in water, all 100 break apart and ionize and form hydronium ions. Okay, so there are 7 strong acids: HCl, HBr, HI, HNO3, HClO3, HClO4, and H2SO4. So hydrochloric, hydrobromic, hydroiodic, the 3 binary acids, and then 4 oxyacids: nitric, chloric, perchloric, and sulfuric. Any acid that is not listed on this table is weak. Alright, briefly let's talk about bases. A base is a substance that will dissolve in water to yield hydroxide ions, OH-. So a common base is sodium hydroxide, or NaOH. Also, it's sometimes known as lye or caustic soda. So strong versus weak bases. Again, strong bases are bases that completely dissolve, so we use a single-headed arrow to indicate the totality of the reaction. Only products remain after the reaction is finished. With weak bases, they partially dissolve, so we use double-headed arrows to indicate the partiality of the reaction. So reactants and products are all part of the final reaction mixture. So there are 8 strong bases: lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, and cesium hydroxide, so the 5 group 1 alkali metals. Calcium, strontium, and barium hydroxide are also strong bases. And for the purposes of our, when we're doing reactions like this, we're going to go ahead and write these as AQ since they're strong bases. Any base not on this table is weak. So a good example of a weak base is ammonia. So ammonia is NH3. You have definitely heard of ammonia before. It's often found in household cleaners. It's also extremely important for crop production since nitrogen is so essential to producing strong crops. So ammonia is used to help fertilize crops. Okay, so let's put these two pieces together and talk about neutralization reactions. Neutralization reactions are reactions where an acid and a base react together and they neutralize one another. They produce water and a salt. So the H from the acid reacts with the OH from the base, and they come together to make water. So what's left behind is the anion from the acid and the cation from the base, and they come together to make the salt. So for example, if we looked at the reaction of hydrochloric acid plus magnesium hydroxide, the H from the acid reacts with the OH from the base to form water. So two H plus ions from the acid react with the two OH minus ions from the base to form two water molecules. So what's left behind? Well, we've got these two chloride ions from the acid and this magnesium ion from the base. So they will come together and form a salt. They form magnesium chloride. So neutralization reactions, it's acid plus base, which forms water and salts. Okay, so let's look at an example problem. Write the balanced chemical equation when a solution of barium hydroxide is neutralized with a solution of nitric acid. So you need to remember your nomenclature rules here. So barium is Ba2+, hydroxide is OH-, so crisscrossing this gives BaOH2. Then nitric acid is based on nitrate, NO3-, so that means nitric acid is HNO3. So this is HNO3 plus BaOH2. Now we need to figure out the products here. Well, make sure they are neutral in charge, so the H is going to come together with the OH to make water, and then what's left behind is barium and nitrate. So Ba2+ and NO3- are going to come together to make the salt, so they'll make BaNO3 using the crisscross rule to balance the charges. So here is our unbalanced reaction. Nitric acid plus barium hydroxide forms water and barium nitrate. So now I'm going to balance the equation. I'm going to place a 2 in front of HNO3 and a 2 in front of H2O. So I would probably start with the NO3 here. You've got two NO3s on the right, only one on the left, so I place a 2 there. Now I'd be left over, I would have these two H's and one O on the right. So to fix that, I'm going to place a 2 in front of H2O here to balance that out. So 2HNO3 plus BaOH2 forms 2H2O and BaNO3. This is my balanced neutralization reaction equation. Then I'll just add in my symbols for state of matter. Water is liquid, and I'm going to treat the rest like they are aqueous here. Okay, now net ionic equations. So neutralization reactions, they do have net ionic equations. So anytime you've got a strong acid and or a strong base, the net ionic equation is always the same. It is always H plus OH- forms water. So that's it. If you've got a neutralization reaction, the net ionic equation is H plus OH- forming water. Everything else is going to cancel out. The anion with the acid, the cation with the base, they are spectator ions. Since that salt on the right side is going to be aqueous, they are going to cancel out. The only time this would ever not be the net ionic equation is if for some reason that salt that's produced is a solid, but it's almost always aqueous, which just leaves this right here as your net ionic equation. Alright, so let's have you try a quick knowledge check question. Select the net ionic equation for the reaction between lithium hydroxide and hydrobromic acid. Alright, and the correct answer here is A. H plus OH- forms H2O. That salt on the right side is aqueous, so this is your net ionic equation. Okay, last thing I briefly want to talk about here are electrolytes. So electrolytes, this is something that I need to cover in this course. It's not actually found in chapter 7, but it fits best with this chapter. If you want to look this up in the textbook, you can find it in chapter 11. So electrolytes, really all you need to know here is that electrolytes, these are compounds that when they dissolve in water, they conduct electricity. So you've probably heard the phrase electrolytes before, probably from like Gatorade commercials. So when we talk about electrolytes in the context of Gatorade or in sports drinks, typically we're talking about things like sodium, calcium, potassium. These are ions that are important to the processes of your cells. So usually they'll put these types of ions in these drinks to help replenish those electrolytes if you're sweating them out during exercise. Now what you need to know is there are three classes of electrolytes. There are strong electrolytes, weak electrolytes, and non-electrolytes. So strong electrolytes there are three types of compounds: ionic compounds, strong acids, and strong bases. So what's similar between these compounds is they all dissolve completely in water. So ionic compounds that are soluble, strong acids, strong bases, when you take those compounds and you put them in water, they completely break apart into their ions. So because they completely break apart into their ions, essentially we just have a very high concentration of ions in solution, and these ions can conduct electricity. So ionic compounds, strong acids, strong bases, they are strong electrolytes because they provide high conductivity of electricity. Weak electrolytes are weak acids and bases. These are compounds that only partially dissolve, so there are some ions in solution, but not a lot. So they conduct electricity weakly. They have low conductivity. Finally, non-electrolytes, these are covalent compounds that are not acids or bases. Something like ethanol, for example. This is a covalent compound. It's not an acid or a base, so it doesn't break apart at all. It does not ionize at all. So we just have a bunch of neutral molecules floating around in solution, so it has no conductivity. So this is all you need to know regarding electrolytes. Strong electrolytes are ionic compounds, strong acids and strong bases. Weak electrolytes are weak acids and bases, and non-electrolytes are covalent compounds that are not acids or bases. Okay, so here are a couple more practice problems for you to try. So pause the video and give these 4 problems a try, and once you have done so, sorry, I forgot to include the answers for these, so I'll go ahead and fix that later in these PowerPoint slides. But all of these problems are being pulled from the Chapter 7 group worksheet key, which you can find on Blackboard. So sorry about that, my mistake. So by the time you are downloading these PowerPoint slides, you should see the answers here again, but you can also download the Chapter 7 group worksheet key from Blackboard. So I'm going to go ahead and split this video into 2 halves since it's a pretty long section. So I'll see you in the second part where we resume section 7.2 and we talk about oxidation reduction reactions.